I'm going to measure the power consumption of the EFM32 processor on my Zero Gecko board, and there are some provisionings on the board to do that. You have this jumper here that allows you to put a current meter in series with the power supply. The only thing you have to do is remove that bypass resistor here of 0 ohms, the P701, so that you can cut the link between power supply and the rest of the board and start measuring. So what I'm going to do now is remove the resistor P701, the 0 ohm bridge, put male headers on the connector. When I'm measuring, I'll put an amp meter in series with the power supply, and if I'm not measuring anything, I'll put a jumper on the connector and it works as before. So now you can see that the resistor is gone and I have this jumper in place. So let's see if the board still works. Yes. So I haven't damaged anything. It's normal that you don't see the voltage and current here because I'm powering it from the battery, and in that case the sensor that's built in the board doesn't work. It only works with the USB powering. So if I do that, you would see that it would show these values again. I'll also check on the schematic what is all powered by this supply to see how we can decide what part of the current goes to the microcontroller and what part of the current goes to other parts of the board.
So what I just done is cut this resistor here, a 0 ohm resistor, and put a header, a male header on this connector. Then when I'm not in measuring mode, I can just put a jumper between these two pins and it works as before. If I want to measure the current consumed by my device, I'll remove the jumper and put an amp meter, a current meter in series. I can't unfortunately measure just the current that is going to the processor because there is more than just the processor here hanging on that very vMCU. And I'm not going too deep into the subject because the EEV blog has already done a similar exercise for the Tiny Gecko board, and he did the same approach by removing this resistor and putting the jumpers in place. But I would like to see on the Zero Gecko board what's all powered from this vMCU. At least the processor here, and that's what we're expecting. And let's go page by page here to see if we can find other occurrences of that vMCU. Yes, it's also going to the push buttons, which would not be an issue generally when they're not pushed. Let's see what's happening on the display. Where is that being sourced from? That seems to come from a different source. Yes, V display. I'll have to check on the power supply page if that V display is coming in some way from the vMCU. This is this power supply, so I couldn't find anything else that is strikingly coming from the vMCU, but I don't see where V display is coming from either, so that doesn't really help. Okay, so a number of these supplies are all coming from vMCU and then derived from there. So there is more than the processor that is getting power from that vMCU. And to test the energy of my device, I'm going to use the E-mode example. That's one of the demos, and this one keeps the processor running at a fixed frequency. You can push a button, and each time you push the button it will switch to a different frequency and you can measure the consumption. So that's what I'm going to do now.
Here is my current measurement setup. I have removed the jumper and I've put the microcurrent in place in the microamp mode, so I measure 1 millivolt per microamp. My meter is in the 2 volt range, which means that at this moment with a program loaded, the processor in use and the display showing, I measure 1.2 volt, which means 1.3 milliamps here. I can cycle through the modes. So the first mode that I'm going to do is 24 megahertz plain use in energy mode 1. So let's press the button and we go to 1.16 milliamps. I'll check a next mode here. I'm not going through all of them, but through a few. The 32 kilohertz energy mode 2. Let's push, and there we drop down to the noise of my meter. I'm getting 10 microamps. And I'm going to do a third measurement, and that is going to be with real-time clock and LCD, if that's there. There we go. So energy mode 2, real-time clock enabled and the LCD display on. Measuring, and that will switch a bit because it is updating the display. So this time it's waking up and doing some updates between 150 and almost 0 microamps.
I'm now going to try if I can do the same exercise using the profiler. So I'll start the program with the profiler here. It's the first time that I do this, so I don't know yet how well it works. So it works perfectly. At this moment the processor is in its current default 24 megahertz energy mode 0. Let's see if I can change that and see what's happening. I'm now going to put it on the low energy mode 2 at 32 kilohertz. And the energy is dropping immediately to about 37 microamps. I'm now going to use one of the other low power modes, so this time I'm going to put it in energy mode 3, and there we get, it's waking up at several times, but average current is about 350 nanoamps. Yet another mode that I'm going to test is energy mode 4. There we go. It's very low, so we are it's counting negative nanoamps. Don't know what I have to think about that, but we are in the noise range here. It's going very low. Let's try one of the other energy modes. Energy mode 2 plus the real-time clock plus LCD powered on is giving me well, you can see here that it's waking up to the full mode several times. That's most likely to do the LCD display. Then it's going above 30 microamps, most likely for the real-time clock, and for the rest it stays under the 1 microamp.
And that concludes my little power measurement exercise. I know that my current measurement mode was dodgy and is not at in any point precise. It gives me ballpark figures, and I'll do with that at the moment. I also used the power monitor, the energy profiler, which works quite well. And we can conclude that it is really a low power microcontroller. Certainly in its specialized half sleep modes it's doing very well and reacting quite fast to wake up again.